So hello and welcome student to this lecture, and this is course number MA412 linear algebra, and today we will discuss lecture number 40. Okay, and today we will discuss another very important normal form or canonical form. It's called Jordan canonical form or Jordan normal forms. Okay, it's after the mathematician Camille Jordan. And like in our last lecture, we discussed the Rational canonical form, which was due to French mathematician Frobenius. And so how many normal forms we learned so far? Normal forms. So we learned about diagonal forms, triangular forms, okay, and then these rational canonical forms or Jordan or Frobenius canonical form, same rational canonical form. Okay, and today we are going to learn very important thing, which is called Jordan canonical form. Okay, Jordan canonical form. Okay, so okay, before that let me just So before telling what is Jordan canonical form, let us try to understand how and why it is important or why we need this thing. Okay. Now recall that suppose I have operators say T on V and over a field F, and I know suppose the characteristic polynomial of T actually splits over V. Okay, over F. So for example, if I choose my F is a field of complex number, then every characteristic polynomial split, right? So in this case, what happened? In this case, we know obviously the Eigen canonical form will be the trivial one, right? But you know there are many options. It can be diagonally eligible or not, right? So what happens if the minimal polynomial, say m of t, so let me write down m of t, minimal polynomial or mt of x, maybe whatever. It's so obviously characteristic polynomial split means minimal polynomial also split, but there might be possibility the minimal polynomial may not be product of distinct linear factor, right? In the case of distinct linear factor, we learn that this will be inside, you can change it to diagonal form, right? But if minimal polynomial split or splits but not into distinct linear factor, then what happens? This is the question. Distinct linear factor. Okay, suppose in this is the case, minimal polynomial split, but the factors are not distinct. So that means what? That means there are at least one eigenvalue, say c, such that x minus c repeats inside minimal polynomial, right? So in this case, what happens? In this case, if you find out the eigen spaces corresponding to distinct eigenvalues, then say for example, so let c1, c2, ck be distinct eigen values of t, okay, with say algebraic multiplicity, say so maybe M1, M2 and Mk. Okay, so what does that mean? That means the summation M1 plus Mk. So this is the dimension of the vector space, right? Dimension of vector space V, which is say n. Okay, now let us assume that the geometric multiplicity. So this geometric multiplicity, so geometric multiplicity of this eigenvalues Ci's are say di. So what are the di? Di's are actually dimension of the eigen spaces, right? ECI's. Okay, so if di's is the geometric multiplicity, and if you know that the this minimal polynomial does not split into distinct factors, so that means this implies t is not diagonalizable, right? Not diagonalizable. If t is not diagonalizable, then what happens? Then obviously then you can find out such at least one eigenvalues whose geometric multiplicity is actually strictly less than the algebraic multiplicity, right? Because we know that this di are always less than equal to mi's, and that linear operator is diagonalizable if and only if di equal to mi for all I, right? For all I, right? And this is in general, this is true for all I 1 to k. Okay, but if the linear operator t does not diagonalizable, then the only option is that at least you can find out one I such that di is less than mi, right? So let me assume that this is C1, C1 equal to C whatever, for which this so D1, which is strictly less than M1, geometric multiplicity less than this. So what does that mean? That means if you want to find out this EC1, which is eigenspace corresponding to C1, so if you take these eigenspaces and take direct sums EC1, EC2, and so on, ECK, then what happens? Then this is not exactly equal to V, because here for example, if I don't know about these eigenspaces, this may be the dimension may be equal to the algebraic multiplicity, but here I know definitely the dimension is less than the algebraic multiplicity, right? So the total dimension will be less than the dimension of, so here the total dimension is less than dimension of V. So that means this direction cannot be equal to V. So this is one way of saying that T is not diagonalizable, right? Then what you can do? So can you have some way to do this kind of makeup? For example, can we have a bigger space than this EC1, such that which will be exact dimension of M1, and then you can have a direct sum decomposition? And the answer is yes. And now we are going to define something called generalized eigenvector. So that the element of these eigenspaces are the eigenvectors of T, right? Now we will define something called generalized eigenvectors, which is actually going to make up for this situation. You can attach some generalized eigenvectors to make this space, the eigenspace corresponding to this C1 is bigger, so that you have a direct sums which is the full space. Okay, now define it. So what is the definition? So we assume that so I am assuming that this is all finite dimensional, otherwise there is no meaning, right? So let V be a finite dimensional vector space, and you have a linear operator T, okay, on V. So in non-zero vector, like eigenvectors are always non-zero. Similarly, so an eigen vector P belongs to V is said to be a generalized eigenvector. Generalized eigenvector of T corresponding to eigenvalue, say corresponding to an eigenvalue, say C, which is element of the field. If what happens if this T minus Ci or something, say, so this is not the same case, so that's not, let me write down something P, some integer. Okay, so this is 0 for some positive integer P greater than equal to 1. Okay, so T minus Ci power P of V, that what does that mean? That means V is actually belongs to the null space of that. V is a non-zero element of the null space of T minus Ci power P, right? Like this, the definition is almost similar to the eigenvector. So for eigenvector, what happens? So T minus Ci, so B has to be null space of T minus Ci, right? Here T minus Ci power P. So what does that mean? That means in general, all eigenvectors are generalized eigenvector, generalized eigenvectors of say level 1 or whatever. So some people say rank also level 1. So what does that mean? That means in that case your P equal to 1. Okay, and if P greater than 1, then it is actually something which is not coming from eigenspaces. Okay, so in general, whenever you have generalized eigenvectors, so you can define something called generalized eigenspace. So the generalized eigenspaces, eigenspace corresponding to space of, say, operator T corresponding to C, eigenvalue C is defined as, so we use the symbol Kc, and this is collection of all vector V belongs to so this is all such vectors such that this T minus C of I or P of V equal to 0 for some positive integer P. Okay, P greater than equal to 1. Okay, so this collection is called the generalized eigenspace, and you can easily note that the eigenspace is actually sitting inside generalized eigenspace, right? And this is obvious because this is, you collect all such P for which this is true, and for P equal to 1 it gives eigenspace. So the eigenspace corresponding to C is sitting inside the generalized eigenspace, right? And if actually so if T is, or rather T is eigenlevel, if and only I should say, so T is diagonalizable if and only if what happens that your eigenspaces are same as generalized eigenspaces for all for uh, eigenvalue C. Okay, then obviously, right? Okay, so then what are the like basic properties of these eigenspaces? So let us try to understand these. Okay, so obviously these eigenspaces are all subspace. Actually, this is very clear. So these cases are subspace of V, obviously containing the eigenspace. Okay, so the eigenspaces are subspace. Okay, and the proof, I think the proof are very easy here. I am not writing the proof. I mean, if you add two things, it will be again, and 0 will be always belongs to KC. Okay, these are simple proof. Okay, and number 2. So if you define the generalized eigenvectors, which are actually linearly independent. Okay, so if you choose two generalized eigenvectors, okay, so the generalized, I mean, for example, if you choose different eigenvalues and general eigenvector correspond to different eigenvalues, they are always linearly independent, and the proof will be similar proof when you prove that eigenvector correspond to distinct eigenvalues are linearly independent. Similar proof will be true here also. So the generalized eigenvectors corresponding to the distinct eigen spaces, eigenvalues are linearly independent. Okay, I think there is some okay, no, I think it is fine. Okay, so the linearly independent, and the proof will be similar. The way we prove it, that eigenvector corresponding to distinct eigenvalues are linearly independent. Okay, and most important thing is that for finite dimension, obviously what we are doing, this you can write down V is actually the sum of this KC1 KC2 plus KC whatever K small. So this is capital K is that symbol for general eigenspaces, and small k is kind of counting that how many sets there. Okay. Okay, so these are basic theorems, and so this is in general it is true. Now question is that how do we attach a Jordan form with respect to this kind of generalized eigenspaces? Okay, so let me define what do you mean by a Jordan form. Okay, so Jordan form or Jordan blocks. Okay, so how do you define? So there are generally two ways to define it. So some people use Jordan form in one method, some people use another method. Okay, so I will tell you both, and I will prepare one method to check similarity with the rational canonical forms, but many books also use the other method. Okay, so we'll write down Jordan block, say block of size 1 corresponding to eigenvalue C, this is nothing but the single matrix containing C. Okay, similarly we write down Jordan blocks size 2. So this is so this 2 cross 2 matrix, this 1 cross 1, this 2 cross 2 matrix. Okay, so I will use the C in the diagonals and 1 in the sub diagonals. Okay, or some people also use the other way. This is 0 here. Some people use C 1 in the up diagonal. This is okay. So this is a convention, and this is not a problem. I will show you why this is not a problem, because if I choose a basis which will gives you this matrix, then if you take the order is opposite direction, then this will give this matrix. So there is no problem. Okay, this is I am writing to make a relationship with the rational canonical form. I will come to that. Now for Jordan 3 cos 3 order 3 will be what? So obviously it will be C0 0 1 C0 then 0 1 C. Okay, so the diagonals are all C, and the sub diagonal means one below diagonals, and super diagonal means one above the diagonals. Okay, sub diagonals are 1. So this is 3 cos 3 matrix. Okay, and obviously in many books people use the other notation, so they use C1 0 0 C1 0 0 C, super diagonals. Okay, so again this is not a problem, this is convention only. You can use any of those things or fix that convention properly. I am going to use this left hand side, this convention. Okay, and so on. So obviously you understood. So if you have a Jordan block of size P, so this will be a P cos P matrix whose diagonals will be on all the eigenvalues, and then sub diagonal will be all ones. Okay, now these are the Jordan blocks. Okay, now if we decompose a matrix in terms of this Jordan blocks, then those matrices are called the Jordan canonical form of the given linear operator. Okay, or the matrix form of linear operator, doesn't matter. Okay, clear? So now so what is Jordan canonical form? Jordan canonical form is that forms where you can write down these in terms of the Jordan matrix. Okay, now let me define some more properties, or maybe I can also start with a example so that you can find out you can understand in details what is happening. Okay, so there are many more properties of Jordan forms. So maybe okay, so let me just do one by one. So, or rather maybe I can start with a example, then it will be easy. So there are two types of example. I mean I can start a basic example first, and then maybe bigger example. So maybe example. Okay, so suppose I have a linear operator whose matrix is of the form say 2 1 2 0. Okay, so this is kind of, you can think A is a map from R2 to R2. Okay, over R2. You can think about it. Okay, and so in this case what happened? In this case you see that it is clear that eigenvalues are are 2 2, which is 2 is repeating, right? Because this upper trigonometry you can easily find out. And characteristic polynomial of A is what? So this is x minus 2, right? The whole square. And obviously you can check then what about this matrix A minus 2i. So A minus 2, so let's check whether A minus 2i vanishes or not. By that you can check what is the minimal polynomial. So A minus 2i is actually 0 1 0 0, right? So this is not equal to the identity 0 0 matrix, right? So what does that mean? That means so this also says that the algebraic multiplicity of 2 is 2 actually. Okay, and this says that x minus 2 is not a minimal polynomial, right? Because it does not vanish. So then what are the options? The only option is that the minimal polynomial of a has to be x minus 2 itself, right? So because minimal polynomial divides the factors polynomial, and x minus 2 is not the minimal polynomial, so x minus 2 whole square will be the minimal polynomial, right? Now x minus 2 whole square is a minimal polynomial. What does that mean? That means that okay, uh, so 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 it means that okay, so I will come to the thing. So I will discuss one more thing, that geometry multiplicity, then I will come to this. So what is geometry multiplicity? So let's do it first. So this actually this degree of the minimal polynomial actually tells that the highest power of Jordan block. So this power is 2 means that you have Jordan block of size 2 cos 2 actually matrix. This is the meaning of that, okay, with respect to 2. But let us come to the geometry multiplicity. So what is the geometry multiplicity of 2? From here, so you see that a minus 2i is of the form 0 1 0 1. So what does that mean? That means the rank of a minus 2i is actually 1, right? This is one linearly independent column of vectors, whatever, and hence you can use rank nullity theorem to say that the nullity of a minus 2i is 1, because 2 minus 1, right? 2 is the dimension of the vector space, which is equal to 1. So null space is 1. So what does that mean? That means the geometry multiplicity di, or what, d of that a minus 2i, it is 1. D equal to yeah. Let me write down geometry multiplicity of, it will be better. So this is the geometric multiplicity of a minus 2i, that is 1, right? Sorry, geometry of 2, I should geometry of the eigenvalue 2, I should say that, of eigenvalue 2 is 1. But as the multiplicity of 2 is 2, already you know that, because 2 appears twice in the characteristic polynomial. But geometry multiplicity is 1. So what does that mean? That means that a is not diagonalizable, right? It's clear, not diagonalizable. Okay. Now if a is not diagonalizable, then what you can do? So you cannot find out a basis which actually consists of eigenvectors of a. That is clear, right? Because if you find out the basis consists of eigenvector of a, then obviously the operator will be diagonalizable, right? Now let us find out what are the, I mean, so the eigen geometry multiplicity is 1 means eigenspace has 1 linearly independent vector, right? What is that? So it's actually 1 0. This is clear from here, because column vector is 1 0, right? So eigenspace has 1 linearly independent vectors, which is 1 0. Yes, so let me write down that. So the eigenspace of 1 is actually generated by the vector 1 0. I mean, you can choose many vector, you can say 2 0 other things. So they are linearly, I mean, they will span the same vector space, right? Same space, subspace. But the eigenspace corresponding to, sorry, E2, not E1, the corresponding to, it is actually spanned by this 1 0. And obviously this E2 is a proper subspace of R2, right? R2 is generated by vector this and this. Okay, so what does that mean? That means so the KC, whatever the geometric multiplicity as a generalized eigenspace, that has to be equal to R2 itself, right? Because geometry multiplicity is 2 and R also has dimension 2. So KC will be equal to this, means what? So you can have a vector in KC, a K2, which is not in R2, and this is this vector. Okay, so this 0 1 actually belongs to K2, right? Now you choose this 0 1 and check what happened. Now if you choose 0 1 and you check that the property that if we apply the operator 0 1 0 0 on the operator 0 1, then what happens? You see 0 1 so 0 1 so 1 0 0 so this is your first vector, whatever this is a v1. Okay, and then so or other v2, it doesn't matter whatever you write down. I will show you the both. This is v1, and if I choose this v1, then I have to choose this is my v2. Okay, and then you see that this t minus 2I of v2 is equal to v1, right? This is that relation. Okay, and in this case, if you choose the basis this v1 v2, and then you see that with respect to this basis the matrix representation of t is t or a, whatever, it doesn't matter what I do. Yeah, so this is my t, and a is the matrix of t corresponding to the standard order basis. And see that with respect to this basis is actually okay. No, so it's v2. Yeah, so I have to check the other way. v2 and then v1. Yeah, so both will gives you the both Jordan blocks. So let me write in for v2 v1, and then or other doesn't matter actually. So let me do it one by one. For v2 v1, what will be the matrix? So when we apply v2 t on v2, so it will be nothing but so it will be nothing, t of v2 is nothing but what? So this is t of you can write down this is as t of 2 minus I of v2 plus 2 v2, right? Yes, because t v2 plus, yes. Now see that t of t minus of v2 is nothing but v1, so you can write down that v1 plus 2 v2, right? Clear? And similarly, if you apply v2 t on v1, so t of v1, so v1 is the eigen vector. See, v is the eigen vector, so t v1 is equal to v1, right? So what will be the matrix representation with respect to this basis? So the matrix representation will be for this is 1 2 so sorry, this is the first, right? So 2 into 1, and for this, so this is 0 times v2 plus 1, so 0 into 2. See, this is the same form, the form I was discussing, okay, of this form. Okay, and if you choose the other way basis v1 v2, so for example, if your basis is b dash equal to v1 v2, then you will have the other form, other option. So how? Because in this case you write down t v1 equal to 2 v1 plus 0 v2, and t v2 you write down as t minus 2 I of v2 plus 2 v2, right? And so this is nothing but v1, so 1 times v1 plus 2 times v2, so the matrix representation will be 2 0 and then 1 2. Okay, so in this case this is this. So the way I define it, either you can use these or this, no problem, but I'm going to do this form only. Okay, so this is clear that the Jordan form is either of those forms, so whatever you convention you do it. But what is important thing is that you can always convert those things to this. And what is the matrix? So to convert this is in this form, what will be the matrix which convert this matrix to this? So that matrix will be v2 v1. So your matrix will be v2 is what? v2 is 0 1 1 0, this matrix. Okay, So obviously now you check that. So this P inverse AP will be exactly of the diagonal form 2 1 0 1 0 2 of this form. Okay, and this is almost obvious, because you just, this means what? This means AP will be P of this matrix, and you check that both are same actually. This is homework, you can easily check it. Okay, clear? So for small such basis vector, it is okay, right? Now if you have for example something bigger, say spaces dimension, that general eigenspace of dimension p, then what you can do? So suppose you have, okay, so the case that general eigenspace corresponding to C, or rather not EC, KC. So KC, which is generalized eigenspace corresponding to C, dimension of that is a P. Okay, or yeah, so should I write P plus 1, then it will be easier, right? Okay, P minus 1 rather, yes. So no, I think P is okay. So dimension is P. So in this case, what you can do? So you can obviously, so in this case you see that the T minus, so the vector which is this null space of T minus Ci, which is actually eigenspace. So this is actually sitting inside null space of T minus Ci square and so on, right? And the last one is last one will be what? Last one will be null space of T minus Ci power P. And why? Because this is the whole space. Because T minus Ci power P. So there is the vectors such that T minus Ci power C. So this is that Kc, the whole Kc, and this is actually, this one is actually EC, the eigenspace, and you have something in between, like, okay, till. And now what you can do? So these are actually proper in this case. So you can find out a vector here which is not inside T minus Ci power P minus 1 and so on. And then you just do these vectors, so you can find out the vector V such that, okay, so what you do? So you find out, so let V be the vector V such that, as what happened, this is V belongs to this null space of T minus Ci power P. So that means that is T minus Ci power P of V equal to 0. Okay, but not does not belong to the null space of T minus Ci power P minus 1. Okay, suppose you choose this vector, and then what happens? Then if you apply T minus Ci on this vector, suppose let me write down this V1. So my V1 equal to this V. Okay, if you apply this on V1, then what happens? Then this is actually element of null space of T minus Ci power P minus 1, right? Why? Because it is in the null space of this, means if you apply this vector, it has to be 0. But this is obvious, because if you apply T minus Ci power P minus 1 on this vector, it will be T minus Ci power P of P1, and that implies 0, because V is the null space of this, right? So this vector V2, which is T minus Ci of P1, yeah, so this vector inside null space of T minus Ci power P minus 1, but it's not inside null space of T minus Ci power P minus 2 and so on, right? So on you can construct, and by that what you can do, you can construct the linear vector V1 V2 and so on, Vp. And now check that they are linear independent, right? The V1, where is the V1? Yeah, so V1 and V2 are linear independent, right? Because so V1 is this and V2 is what? V2 is T minus Ci of V1. They are linear independent. If they are not linearly independent, if they are linear dependent, then you can find out the counter. You can find out the problem. Why? Okay, so let me just tell you. For example, if there is some alpha 1 plus alpha 2 of T minus Ci of V1 equal to 0, in this suppose they are not linearly independent, they are 0, then what happened? Okay, so maybe you can say one more thing. TV, no. Okay, so let's suppose this is 0, then what you can do? So you can apply applying the operator T minus Ci power T minus 1 both sides. If you apply it, then what happens? Then in this equation will become alpha 1 times T minus C1 power T minus 1 of V1 plus alpha 2 times T minus Ci power P of V1 equal to 0. But this is already 0, you know that, because V1 is an alpha of that. So the only remaining part will be this times this, but this is non-zero, you also know that by definition. This implies alpha 1 equal to 0. If alpha equal to 0, you can plug into this equation star and you find out the beta alpha 2 is also 0, right? So they are all linear independent. So thus this will forms a basis which is linear independent, right? I mean, this is linear independent and basis for, okay, so this is basis for this generalized eigen space, okay, KC, and done. So now with respect to this basis, what is the representation of the linear operator T? And that is obvious because you can now write down easily. For example, if you apply T on V1, you know that you can write down the T minus this C of I of V1 plus C V1, right? But this is what? This is nothing but V2, C V1. Okay, is clear? Similarly, T V2 you apply, this is V3 plus C V2 and so on, right? So then what will be the matrix? So this is the first vector, right? So C, and the second vector 1, and everything is 0. So 0, 0, 0, 0, 0. Similarly here, what is happened? So coefficient of V1 is 0, so 0. Coefficient of V2 equal to C. Coefficient of V1 is equal to 1, and everything is 0. So 0, 0, 0. So what does that mean? That means diagonals are C and sub-diagonals are 1 and everything is 0. Okay, and this is the Jordan block corresponding P cross P Jordan block, right? Okay, so so this is the method to find out Jordan canonical forms, and also now the question is that what will be the biggest Jordan block? So for that, let me tell you. So suppose you have an eigenvalue C and geometry multiplicity is say algebraic multiplicity is say M. Okay, so general fact, say algebraic multiplicity say M, and geometric multiplicity is equal to say D of some corresponding to some eigenvalue C. And then what happens? Geometry multiplicity tells us how many blocks are there, how many Jordan blocks are there. For example, when D equal to M, the number of Jordan blocks are M, and and so you have M cross N matrix, and you have number of Jordan blocks. M means every Jordan block has to be a 1 cross 1 block, and hence the matrix will be diagonalizable, right? And that is obvious. When D equal to M, then matrix is diagonalizable, right? But otherwise, the geometry possibility implies the number of Jordan block is this D, and the geometry possibility, right? The question is that what is the biggest Jordan block? This is the, I understand this many Jordan block will be there. But what is the biggest? Means that largest size of Jordan block, and that is coming from the I already said minimal polynomial. So we check what is the power of minimal polynomial, right? So the power of minimal polynomial. So if that order of the the minimal polynomial is the largest Jordan block. Okay, in general, if the matrix is diagonalizable, then minimal polynomial has all linear factors, and hence every Jordan block is 1 plus 1, and that is also the proof. Okay, so both those are okay. Now let me discuss one example, maybe in general example, and see what happening here. So for example, suppose I have a matrix say of this form. So maybe another example. Okay, the matrix say A or whatever T, doesn't matter, T with respect to standard order basis of R3. So this is a map from R3 cross R3 to R3 over R3 over R, and this is something like that, say 1 1 0 2 1 minus 1 0 2 1. Okay, suppose this is my matrix, and I want to find out the Jordan form of this matrix. Okay, now let us first see diagonal or not. If the diagonal level, Jordan form will be the trivial, the diagonal form, right? What we can say about this? So first let us check what are the eigenvalues and eigenvectors, and you can check actually eigenvalues are actually all 1 actually. So this is not difficult problem. You check what is this determinant of x I minus a, and this is exactly x minus 1 2 0 sorry minus 2 0, and then minus 1 x minus 1 minus 2, and then 0 plus 1 x minus 1, right? So the determinant of this matrix is the characteristic polynomial. This is nothing but the characteristic polynomial of T, right? Now see the 0 is here, so so it is enough to find out what is happening. Okay, so here, okay, so now so this is this, so this time this will gives you that characteristic polynomial, and since characteristic polynomial is nothing but x minus 1 whole cube, right? Okay, and so obviously you can ask what is the minimal polynomial. So what does that mean? That means that algebraic multiplicity of 1 is actually 3. Okay, now what is the geometric multiplicity? Means that we will find out the eigenspace, right? So first let us find out what is the eigenspace. So so a minus 1, a minus I. What is a minus I? How it look like? So this look like the matrix of this. So 1 1 1 will cancel. So a minus I will be 0 2 0, and then 1 0 2, and then you will have 0 minus 1 0. So this is a minus I, right? And now it is clear that this first row and last row, or first column or second last column, they are actually independent, right? And hence rank of a minus I is actually 2, because there are 2 linearly independent rows or columns, right? And hence this nullity A minus I is 3 minus 2, right? Because 3 dimension, so this is 1. So nullity is 1, and this what that means is this is geometry value, right? So geometry value is 1 actually. So what does that mean? That means there will be one Jordan block only, and obviously a 3 cross 3 matrix, one Jordan block means the highest Jordan block will be exactly 3, and that means also minimal polynomial has degree 3. But this you can easily find out also from here, because if you want to find out what is a minus I whole square, and you take that square, and it is not difficult to check that a minus whole square will be of this form. So this is 2 0 minus 1 0 0 0, and then 4 0 minus 2. Okay, this is okay. Okay, so so what does that mean? That means you can check that what is happening for a minus I whole square. So a minus I whole square, you see that there is only one linearly independent rows. Because this is 0, and the first row and third row is also dependent, or you can say column wise also, first column, third column is linearly independent. So only one linearly independent column, hence so you can say more here, rank of a minus I whole square equal to say 1, and hence nullity of a minus I whole square equal to say 2, right? So it has two vectors. Now do one by one, find out eigenvectors, and generally eigenvectors of what are 2, we will all find out. So for eigenvectors, a minus I is this. So this is so one thing is clear, or maybe let me find out. Not I should not say clear. So for eigenvectors of this matrix, so this is related in the matrix 0 1 0 and 2 0 minus 1 2 0 minus 1 0 2 0, right? And if you have eigenvalues, then and if it is the kernel of this map, then it has to be this has to be 0, right? 0 0 0. So this vector, any vector which will be eigenvalue, will be inside the kernel of this map. So this is 0, right? So what does that mean? That means what are the equations? So 2x2 0 times x1, yeah. So this is 0, and then so that means this implies x2 has to be 0. x2 has to be 0, and from second to one you have x1 plus 2x3 equal to 0, right? So what does that mean? That means yeah, so x2 has to be, x1 has to be minus 2x3, right? So what does that mean? That means you know how the eigenspace look like. So eigenspace is of the form x2 will be 0 and x1 will be, yeah. So eigenspace corresponding to eigenvalue 1 is generated by the vectors minus 1, so 2 minus, yes. So this is the form 2 0 minus 1. Okay, so this is the eigenvectors which actually generates the eigenspace, right? It's obvious from here, because x1 and x3 has this relation. So if you put x3 equal to minus 1, then x1 will be 2. So 2 minus 1 and x2 has to be 0, right? This is eigenspace. Now you want to find out generalized eigenspace. So for generalized, so let us find out general eigenvectors. First, eigenvectors of rank 2, and that is coming from here, because here the nullity is 2 means there are 2 such vectors, right? But we already find one vector. Every eigenvector is general eigenvector. So this is already one candidate. Now we have to find out another candidate. So that candidate, how do we get the candidate from here? Okay, so I have to find it from here. So 2 0 4 0 0. Okay, so So the matrix 2 0 4 0 0 0 then minus 1 0 minus 2, is that right? This is the matrix for a minus I whole square, right? Now you find out again the vector x1 x2 x3 such that is 0 0 0, and first relation is 2 x1 plus 4x2 4x3 equal to 0, but this is obvious. This means x1 equal to minus x2, that is coming from this. Okay, I don't care. So and last one is what? Last one is minus x1 minus 2x3 equal to 0 again. So x2 can be anything actually. Your x2 is here anything. The first one x2 was 0, here x2 can be anything. So next vector, so this is my vector, say v1, and next vector I will choose what? So this vector is what? This vector is anything inside the space. So this is 0 1 0, right? Because null space of this null space of t minus I whole square is generated by the vector 2 0 minus 1 and then 0 1 0. Why? Because you see the first equation tells you that it is this eigenvector, and x2 is independent, so that means you can choose any x2. So I can choose 0 1 0, x2 can be 1, right? So this will be my new second vector v2. Okay, and not only that, you also check that this vector has the same property. If we apply this vector, it will come this vector with the matrix. So you can check that the matrix, whatever the matrix T, which is 1 1 0 2 1 minus 1 0 2 1. If we apply 0 1 0, and then it will be exactly 1 2 and 0. So 1 1. So 1 is 1 times 0 0 1 into 1. 1 minute. Not t, t minus I. T minus I have to apply, right? Not t. This t minus I. So what is t minus I? T minus I is 0 2 0 1 0 2 0 minus 1 0, right? So now if we apply this, you see what will be 0 2 0 and then 0 0 0 and then 0 minus 1. Yeah, exactly. So what I said, so my so v2 is nothing but t minus I of v1. Sorry, v1 is nothing but t minus I of v2, right? Okay, so yes, and now so this is I am choosing the other way. This will give you the upper form actually, not the lower general form. Yeah, but no problem, you can choose the basis other way also. Okay, exactly opposite way. So for last one, so now okay, so you already know that t minus I whole cube is 0 vector, right? This is because minimal polynomial is x minus 1 whole cube. So what that means, that means null space is full space, right? Null space of t minus I whole cube is the full vector space R3. So now we need to find out a vector which is not in the null space of t minus I whole square. So outside that. So how to find out the vector which is outside this? And then obviously you can choose many ways, but it is clear that if I choose the standard vector 1 0 0, so v3, if we choose v3, now you see that v3 is inside R3, which is obviously null space of t minus I whole cube, but not inside null space of t minus I whole square, right? T minus I whole square. And so what is my v3? v3 is 1 0 0, the standard matrix. Okay, now obviously my basis is what? My basis is this v1, v2 and v3. With respect to this basis, the Jordan block will be exactly upper triangular form. So what does that mean? That means this is 1 1 1 1 0 1 and 0 0 0. Okay, now if you change the basis, if you write down the basis beta is v3, v2 and v1, then it will be the lower form, the whatever I like. So 1 1 0 0 1 1 0 0 1. Okay, so whatever you choose, you can choose either this or that. Okay, doesn't matter. Okay, so this is the basic idea of how to find out Jordan canonical forms, and with respect to this basis, this. So what does that mean? That means the matrix. If you write down P the matrix, then P will be the matrix this whose column vector will be v3, v2 and v1. With respect to this matrix, P inverse A P will be the Jordan form. This Jordan form maybe say J, it will be J. Okay, clear? Okay, and if you write down instead of P v2 v1, if you write down v1 v3, then the Jordan form will be this one, which is J dash in that case. Okay. Okay, so I will stop here for today's lecture.